In this tutorial, you will learn how to configure the CFD model for a coupled CFD and DEM tablet coder simulation. We begin by setting the simulation units to SI units. Next, we import the geometry of the tablet coder. Using the Boolean CAD body subtraction tool, we create the fluid domains. These include the main drum, the inner stationary cylinder, and the outlet plenum. We then apply mesh controls to selected faces. The mesh size on the nozzle surfaces must be finer than the general outer mesh. Select all outer surfaces of the drum and the outlet plenum, and in the mesh control settings, apply a mesh size of 20 mm. Next, hide the outer surfaces to easily access the inner components. To do this, select the desired surfaces and press the H key. With the outer surfaces hidden, select the surfaces of the inner cylinder. It's important to note that there are two sets of cylinder surfaces here. Because the neighboring bodies have overlapping boundaries, you must select both sets. Apply a mesh size of 10 mm to these surfaces. Next, select the nozzle head surfaces for both nozzles. Apply a fine mesh size of 1 mm to these surfaces. Finally, select all remaining nozzle surfaces and apply a mesh size of 3 mm. You will be prompted to replace the existing mesh control on the nozzle heads. Select No to preserve their finer mesh setting. A tetrahedral mesh is generated for the fluid bodies. We first set up a flow solution. The multi-phase model is set to Eulerian EDEM bidirectional. We specify the time step and final simulation time, and enable heat transfer and species transport. Next, we create a coupled solution, with the coupled physics set to flow plus EDEM external. A result request is added with an output time interval of 1 second. We then activate the flow solution as the current solution. A new material is created, and air is selected as the carrier fluid. All bodies are assigned to the newly created material. We also assign the mesh bodies to the flow solution. Interfaces between the different bodies are now defined. First, we define the interface between the drum and the outlet plenum. After selecting the interface faces of the drum, we temporarily hide it to easily select the interface face of the outlet plenum. Next, we define the interface between the inner cylinder and the drum. Since the inner cylinder contains the nozzle boundaries, it must remain stationary while the drum rotates. This requires separate bodies and an interface between them. Ensure that you select the cylinder surfaces that are common to both bodies. We set initial conditions for temperature, velocity, pressure, fluid phase, and species concentration. The outlet boundary condition is defined. The walls of the drum and the outlet plenum are set with a convection boundary condition. Additionally, make sure the water vapor species flux is set to 0. To access the nozzle boundaries, we will hide the outer bodies and their associated surfaces. We define the pattern air inlet for the nozzles. This is set to be normal to the boundary, and we also specify a temperature and water vapor mass fraction. Next, the atomization air inlets are defined. Since the velocity direction is different for the top and bottom inlets, two separate boundaries are created. The atomization air is defined to flow towards the nozzle center from each side. To account for the nozzle's 45-degree tilt, the top air inlet is oriented in the positive Z direction, and the bottom air inlet is oriented in the positive Y direction. A zero flux boundary condition is applied to the nozzle walls. It is important to set wall boundary conditions for interface boundaries, as the interface definition alone does not count as a boundary condition. We set the active type to no interface, so the wall boundary condition is applied only where there is no interface. For the inner cylinder, this boundary condition will never be active because it is always an interface ensuring proper boundary enforcement. We also set wall boundaries for the inlets, again with no interface as the active type. This ensures that inlet velocity is applied where the inlet is exposed and the face acts as an internal surface when covered by the outlet plenum. The velocity in cylindrical coordinates is defined for the boundary, including non-zero radial and tangential components. The axis of the cylinder is defined by selecting an edge from the geometry. Since the drum is rotating, inlet velocity directions must also rotate accordingly. This is handled using a sine series multiplier with the frequency and phase set to match the rotation. The inlet temperature is specified. Then we define a linear rotational motion for the drum body. Finally, the coupled solution is transferred to EDEM.